Chapter 3 of the Recurrent Neural Networks course. Section 3 to 4, Summary Equations of the Basic Recurrent Neural Networks. Let us summarize the set of equations to be used in computations. The architecture of the basic recurrent neural networks is given in equation 3.41, as we have seen them before. Note that the adaptive parameters are now indexed with the iteration, for example, mini-batch, index k to denote when these parameters are updated during training. Furthermore, these parameters are expected to converge to a near constant at the end of the training process, for example, after a certain number of epochs. The iteration index k denotes the mini-batch or the number of samples, where each sample is a full sequence over the finite horizon training duration. Specifically, a sample is composed of the input label pairs, s_t, y_t, over the finite time horizon, for time index t ranges from 0 to n. We thus use the time index t along each time step of the sample sequence over the finite horizon, for t from 0 to n, while the parameter update iteration index k per one, or multiple, full sample sequence as illustrated in the figure on the slide. For a given iteration index k, this recurrent neural network propagates forward for a given, or chosen, initial condition x_0, and a sequence pair, s_t, y_t, to generate the state x_t. The corresponding hidden nonlinearity h_t, and the output z_t over the sequence duration t from 0 to n. The output error sequence, that is, z_t minus y_t, is then determined. The backpropagation costate equations need the final costate and the output error sequence to generate the costates lambda_t backward in time t from n to 1. Here, the final costate is expressed as the equation shown on the slide. We have explained in equation 3.34, the matrix sigma'_n is the derivative of the nonlinearity vector sigma_n expressed as a diagonal matrix of element-wise derivatives of the corresponding scalar nonlinearity. And as we mentioned in section 3.3, for computational efficiency, it may also be represented as a vector of derivatives that pointwise multiplies the transformed error vector as a vector-Hadamard multiplication. Let us compactly express the output error sequence over the finite time horizon duration, as shown in equation 3.42. Recall that the final time boundary condition of the costate is given by equation 3.43, and that the backpropagating costate dynamics are expressed by equation 3.41, which will be further explained in appendix 3.2. From appendix 3.2, which we will explain later, the state equation parameter gradient changes at each time instance t, for t from 0 to n1. And without regularization, are given by equations 3.45, 3.46, and 3.47. Note that these equations are partial gradient of network parameters. Similarly, from appendix 3.2, the parameter, weight and bias, updates in the output equation at each time instance t, for t from 0 to n, and without regularization are shown in equations 3.48, 3.49, and 3.50. Usually, these parameter change contributions at each t instance are summed over t over their time horizon to provide one change per sample, that is, a sequence over the time horizon duration. And, usually, these parameters are updated after a batch of samples for each iteration indexed by k during training. Once the iteration parameter updates converge to near constant values, or iterations reach a preset number of mini-batches or epochs, then training is stopped and the parameters are frozen in order to provide a finalized basic recurrent neural network model. This final model with fixed parameters is then ready for testing or inference. Thus, for each parameter, we may accumulate the parameter change contributions over the time horizon to obtain their updates as shown in equation 3.51, 3.52, and 3.53. Note that the update here is over the time index from 0 to n-1, which is expressed in the summation form in these equations. Similarly, the parameter, weight and bias, updates in the output equation at one iteration can be done over the time horizon as shown in equations 3.54, 3.55, and 3.56. Remark 3.7 The above parameter update expressions are the sum of the contributions over the time index t, that is, over the entire sequence, which is proportional to the time averaged value. we shall emphasize that this is only one choice. Observe that it is equivalent to using the mean, or more precisely, the time average, of the gradient changes over the sequence of equations, 3.45, 2, 3.50. Note that the hyperparameter rate absorbs any scaling due to the number of elements of the sequence. The mean, however, may be small or even zero, while some gradient changes at some time indices t may be relatively large, in absolute value. In fact, this is one explanation of the vanishing gradient phenomena. That is, even though the cost-state and output error sequences are not vanishing, the gradient changes using the mean as in equations 3.51, 2, 3.56, are. Remark 3.8 Other choices to explore are to use the median, the minimum, or the maximum of the changes over the gradient change sequences, equations 3.45, 2, 3.50. Moreover, the change in power or strength in the sequence of changes is best captured by the variance, which should influence the learning rate in many ways. Thus, there are alternate possibilities of the iteration update laws for recurrent neural networks besides the ones in equations 3.51, 2, 3.56. Remark 3.9 The vanishing and exploding gradients can be explained easily by investigating the update equations 3.51-3.56, and the backward cost-state dynamics equations 3.43-3.44. Assume we have a network which is able to learn sequence-to-sequence mapping. This is an existence property, that is, there exist sets of parameters that enable the sequence-to-sequence mapping for the network. By their nature, the state and cost-state equations form an unstable saddle point dynamics. As the cost-state and the error signals are used in the expression of the gradient updates, the gradient will continue to relatively grow unbounded. This process will make the state and cost-state grow unbounded, leading to the so-called exploding gradient phenomena. This is another justification for the error backpropagation in addition to the fact that we use the final cost-state value to trigger the cost-state sequence backward in time. Remark 3.10 The leading negative sign in the update laws equations 3.452, 3.50, can be fully absorbed by redefining both the variables et and lambda_t to be the negative of what they were defined above. This can be easily done by defining the loss function as y_t minus c_t, instead of z_t minus y_t. Remark 3.11 In the update laws and the iterations, one must use sufficiently small a to avoid the occurrence of numerical instability, near convergence, while allowing the iteration process of the parameter update to be sufficiently small. The presence of the dominant stable linear term in basic recurrent neural networks would ensure that, for bounded parameters, the network is bounded input bounded state stable and thus the states, costates, and consequently, the gradient would not grow unbounded. This ensures the basic recurrent neural networks can steer the error in the cost-state sequences towards zero during training. Here, we make some concluding remarks. This chapter introduces the simple recurrent neural networks and identifies the internal state and the hidden activation function. It also shows the simple calculations of the backpropagation through time for the parameter update during training for supervised learning. However, backpropagation through time does not teach, for example, how to incorporate unsupervised loss on the internal states. Thus, this chapter follows up with an improved design for a basic recurrent neural network that slightly adjusts the simple RNN in order to improve the dynamic behavior. This entails a basic recurrent structure and an output layer with sufficient parameters to enable a flexible bandpass filtering suitable for general RNN applications. The framework adopts the classical constrained optimization and calculus of variations to derive the generalized backpropagation through time and stochastic gradient parameter update laws. This principled approach enables ease in incorporating general loss functions. The presentation clearly shows the correspondence of the backpropagation through time approach with applying the classical Lagrange multiplier method and constrained optimization. One may choose a loss function as a sum of differing, supervised or unsupervised, loss components on any variable in the recurrent networks, namely outputs, states, or hidden units, that is, nonlinear functions of the states, and also explicitly on the parameters. It further shows that the usual sum of contributions of changes to the parameters inherent in the backpropagation through time approach is only one form of update, and it could be a source of the vanishing gradient phenomena. Finally, this chapter explains the exploding gradient phenomena due to either numerical instability or the instability of the network's state and the cost-state dynamics manifesting themselves in the gradient update laws.